introduction and inviting me to this nice webinar. Let me share my slide. Okay. Okay, let me begin. So I will talk about search for parity-violating physics in the polarization of the cosmic microwave background, so-called cosmic birefringence. This talk, this talk is based on this paper published last November 2020. Here we said we find a hint of cosmic birefringence with 99.2% confidence level. This corresponds to the statistical significance of 2.4 sigma, yeah, which is smaller than the G-2 anomaly. And yeah, this work is the collaboration with Eiichiro Komatsu in MPA. And we worked for about 2 years to, for, to realize this analysis. At first, in 2019, we wrote the original paper to describe the basic idea, methodology, and validation using the full sky data of CMB map, simultaneous determination of miscalibration angles, and cosmic birefringes, where we showed new way to measure cosmic birefringes. And in this second paper, I developed the methodology to include the analysis of partial sky observation. And in this third paper, we included cross-frequency spectra to improve the sensitivity to cosmic birefringence. And this method is actually used for analyzing Planck's PRC data, 2018 data. At first, yeah, let me talk about the cosmic birefringes. What is cosmic birefringes? It's like the universe filled with birefringent material, such as sapphire crystal. If the universe is filled with a pseudoscalar field phi, for example, an action field, which coupled to the electromagnetic tensor via Chern-Simons coupling. Yeah, phi is pseudoscalar field in F mu nu is electromagnetic tensor, F mu nu tilde is its dual, and this G phi gamma is a coupling constant between phi and electromagnetic fields. In Lagrangian density, this F mu nu term is already exists in standard model, which only shows, in electromagnetic fields, which corresponds to the parity-even field. However, if there is Chern-Simons term, which produce parity-odd electromagnetic fields. And yeah, phi is pseudoscalar, so parity is odd. F mu nu tilde is parity odd. So in total, this term is parity even as a whole. And if this term exists, what happens to photons? If when photon travels in the, for example, the vacuum filled with birefringent material, the linear polarization plane of photon is rotated by angle beta, related to G phi gamma over 2 times the difference of field values between the observer and the emission point. So the difference of field values rotates the linear polarization plane of photons by angle beta. And what is the motivation of this pseudoscalar field? Yeah, that is the dark components in our universe. The universe energy budget is dominated by 2 dark components, dark energy and dark matter. And we know that the weak interaction violates parity. So why should the laws of physics governing the universe conserve parity? We use the cosmic microwave background to test this. This is a temperature anisotropy map created by ESA's Planck satellite mission. CMB, cosmic microwave background photons, were emitted 13.8 billion years ago at the last scattering surface, where electrons and protons combined and became neutral. And the linear polarization is like this. This black lines show the linear polarization of photons of CMB, which is determined by ESA's Planck satellite. And in the standard cosmology, we know the initial rotation angle beta to 0. So if we observe the beta at the Earth, near the Earth, we can test the parity violation whether beta is non-zero or not. And for the particle physicist, which is possible when we search the cosmic microwave background, dark energy or dark matter. I have been asked this question many times. So this is the sensitivity to action-like particles, coupling constant G against the mass of action-like particles. The most sensitive region is about when mass is equals to the present hub H0, about 10 to minus 32 electron volt. It's almost like the dark energy. And when the mass becomes smaller, the sensitivity becomes worse because of small mass of action-like particles, the oscillation of field becomes slower and slower. So the difference of the field values between the last scattering surface and observer becomes smaller, and we lose the sensitivity when mass becomes smaller. And when mass becomes higher, around this area, 10 to minus 26 electron volt, the sensitivity becomes damped because of the thickness of last scattering surface. The oscillation of field, action-like particle fields, becomes faster, and it oscillates during the last scattering surface. So the Birefringence effect becomes smaller, and because of the damping. And for the details of action-like particles, see Marsh 2016 and Ferreira 2020. They review the action-like particles. And this figure is from our theory paper, Fujita Minami, Murai, and Nakatsuka 2020. And maybe last month, it was published in PRD. Okay. So let's move on to how we measure the linear polarization of CMB signal. We measure linear polarization with two orthogonal parameters, Stokes Q parameter and Stokes U parameter. Q shows the polarization horizontal and perpendicular against the coordinate. So this horizontal one shows Q is negative and U is 0. This perpendicular one, Q is positive and U is 0. And with U, we measure the 45-degree tilted one. So this one shows Q is 0 and U is negative. This one, Q is 0 and U is positive. So using these two orthogonal parameters, we can measure all the linear polarization of photons from the sky. However, in real analysis, we decompose these Q and U to E and B modes, so-called E and B modes. it's like a Fourier transformation. We transform Q and U from real space to wave number space. E mode shows the horizontal and perpendicular linear polarization against the wave number vector. B mode shows 45-degree tilted one with regard to wave number vector. And these E and B modes are only jargons in the CMB community and completely unrelated to the electronic and magnetic field of the electromagnetism.
Sorry, can I ask a naive question?
Yes.
I thought the polarization always has to be perpendicular to the wave. I mean, to the direction of motion of the photon, or
Yes.
is this wave number something else here?
This wave number is like a scale in this space, in this map. L equals 1 means this type of oscillation, plus, minus. L equals 1 means this kind of wave.
Okay. Yeah, okay, but if you have a wave number direction, then you have a wave number vector in some way. And what is that then? Is that supposed to be the, I mean, apparently it's not the direction of the light, but yeah, what is it?
It's not it's different from the direction of photons. It's only the scale of. So yeah. These are two-dimensional space, okay? In real space, these are two-dimensional space. So to identify one point, one position, we need one vector. So in Fourier space, we need Lx and Ly, which corresponds to x and y in real space. Like that, we have a wave number vector. Okay. It's like the vector in Fourier space. Okay.
But I mean, how is it then guaranteed that all those polarization directions are indeed perpendicular to the travel direction in real space? If this wave vector is essentially decoupled from the from the real space.
Sorry, I'm not sure your question. However, yeah, because the photons were emitted very far, the place which is very far away from us, then all the photons becomes a plane wave. For the plane wave, so they only have the perpendicular linear polarization against the incoming vector. Okay.
Okay, thanks.
Mm-hmm. So yeah, for the plane wave, yeah, we can measure linear polarization only with these two orthogonal parameters. And the CMB signal is plane wave. And yeah, how these parameters, E modes and B modes in Fourier space transformed under the parity flip. So E mode, when they are flipped, horizontal one becomes horizontal one, and perpendicular one is perpendicular one. So E mode is parity even. However, 45-degree tilted B mode is flipped to minus 45-degree tilted. Minus 45-degree tilted B mode becomes 45-degree tilted B mode. So B mode itself is parity odd. And we evaluate some cosmological information. We extract cosmological parameters from the two-point correlation functions, because only this one parameter follows the Gaussianity, so it only fluctuates from -1 sigma to 1 sigma or so. So we cross-correlate, we take two-point correlation functions to evaluate some cosmological parameters. And you may hear E-mode power spectrum. That is the E-mode autocorrelation. B-mode power spectrum means B-mode two-point cross-correlation. So these are, because these autocorrelation, EE and BB, they show parity even. And this T is the temperature anisotropy of CMB signal. So it's only a scalar value. So of course, parity even. And E mode is parity even. In total, TE cross correlation is parity even. The others, TB and EB, are not invariant. E is parity even, B is parity odd. So in total, EB cross correlation is parity odd. So we can use these variables to probe parity violating physics. And in this study, we only use EB cross correlation. So this is a typical figure that you find in many talks on the CMB. I will show the power spectrum. So this is a temperature anisotropy, which this oscillation is created by sound waves of the early universe. And this is E-mode power spectrum. And this black solid line shows the B-mode power spectrum created by lensing effect, which is from the E-mode. And this E-mode power spectrum is distorted with lensing potential, and which induce the B-mode. And this thin solid line shows the B-mode from the primordial gravitational waves. A gravitational wave from inflation, if any. So in most CMB experiments, they are searching this primordial gravitational wave to test inflation. And our focus is the EB cross spectrum. There is no EB cross spectrum because in the standard cosmology, parity is, we assume parity even. So EB should be 0. So the EB cross correlation is always not shown in this kind of typical figure.
So that means even if we have primordial gravitational waves, EB is still 0?
Yes.
Oh, very good.
If there is some like a chiral gravitational wave which violate parity, that would induce EB cross correlation. But that is different from the usual single field through model inflation. And so how we measure the EB cross correlation from the cosmic birefringence. So the linear polarization plane is rotated by beta. So that means cosmic birefringence convert E and B mode. So the emitted E and B modes are here. They are rotated by rotation matrix, cosine 2 beta minus sine 2 beta, sine 2 beta, cosine 2 beta. So E and B modes are rotated by this rotation matrix, and we observe this left term, rotated one. And this too means E and B modes are spin-2 variable. So yeah, in power spectra from this equation, we can derive CLEB observed can be related to EE minus BB power spectra over 2 times sine 4 beta. And this CLEE and CLBBs are the emitted power spectra. And the last term shows the CLEB at the last scattering surface times cosine for beta. So in the standard cosmology, we can assume this to be 0. And yeah, we need to assume this initial power spectra from some cosmological parameters. So traditionally, one would find this beta by fitting this CLEE CMB minus CLBB CMB to the observed CLEB power spectrum using the best fitting lambda CDM model. Yes. So assuming the intrinsic CLEB to be 0, we can measure the rotation angle beta. However, Chao et al. 2015 and Minami et al. 2019, they showed that we can measure the angle only with observed power spectra. With some calculations from the same equation at the beginning, with some a little bit complicated calculation, we derived the equation. Observed EB power spectrum can be related to CLEE observed minus CLBB observed, and the coefficient is tangent for beta over 2, which is slightly different, and plus an intrinsic EB cross correlation term. We can assume this to be 0. So using this equation, we can determine beta without assuming the initial power spectra of CMB. However, there is the biggest problem, is calibration of detectors. If satellite is rotated by alpha, but we do not know it, it's like a schema. It's a schematic figure of polarization sensitive detectors on the focal plane of this satellite. We assume that they are installed to sense linear polarization in this direction and this direction. If there is miscalibration and they are rotated by alpha, the real detectors are installed like this are rotated by alpha. However, we do not know the real rotation alpha. If there is this alpha, we can only measure the sum alpha and the cosmic birefringence beta. We can only measure this alpha plus beta. So we have to break the degeneracy to measure beta. Let me show some results from the past measurements. Measurements of alpha plus beta. At the first measurement of cosmic birefringence, that result is minus 6.0 plus minus 4.0. This is from the statistical uncertainty. And for example, the Planck collaboration reported that value is 0.31 plus minus 0.05. So the value is 6 sigma. So phi not yet discovered, that is because the degeneracy of alpha and beta. So to claim the discovery or measurement of beta, we have to determine alpha with some way, calibration on the ground, or calibration using some linear polarization of celestial source. When we include the systematic uncertainty from the calibration, Planck collaboration reported the uncertainty is 0.28. So they claim angle is 0.31 plus minus 0.05 plus minus 0.28. So the systematic uncertainty is very large, and that limits the measurement of beta. And yes, in some experiments, they did not evaluate or calibrate the rotation, detector rotation. So there's a question marks. So there are some ways to determine this alpha. One is using celestial source. However, if we use celestial source, the calibration uncertainty is 0.27, which is comparable to this 0.28. So we cannot reduce the uncertainty. And when we use some apparatus like a wire grid on the ground, that might be the uncertainty of 1.0 degree for the Planck pre-launch paper. That is very large. So we need other ways to reduce this uncertainty to measure cosmic birefringence more precisely. Here comes the key idea. The polarized galactic foreground emission as a calibrator. Polarized dust emission within our Milky Way is like this. They are emitted right there. It would not be affected by the cosmic birefringence. So we can use this polarized dust emission within our Milky Way to calibrate the detectors. So yeah, searching for birefringence, including the polarization signal from galactic foreground. So miscalibration of the polarization angle alpha rotates both the foreground signal and CMB signal. But cosmic birefringence beta affects only the CMB signal. In coefficients, E mode and B mode, E mode of foreground is rotated by alpha, and CMB E mode is rotated by alpha and beta, and these are the noise terms. And B mode is also similar. B mode observed is from foreground B mode rotated by alpha, and B mode CMB signal rotated by alpha plus beta. From this equation, we derived new equation. CLEB observed can be related to tangent for alpha over 2 times difference of observed EE minus BB, plus sine for beta, here comes cosmic birefringence angle beta, over 2 cosine for alpha, times difference of power spectra of CMB signal. And this is known accurately from the lambda CDM model. And other residual terms. One is intrinsic EB cross correlation of foreground, and the other is EB cross correlation of CMB signal. We ignore the intrinsic EB cross correlation of the foreground and this CMB. However, the latter, this one, is justified to assume. We can assume this to be 0, but the former is not. We will revisit this important issue at the end. However, if we ignore both these terms, we can determine alpha and beta simultaneously using the different multiple dependency, L dependency of power spectra. To determine alpha and beta simultaneously, we prepared this kind of likelihood. This is only for the single frequency case and full sky data case. This numerator is from this equation. Left hand side minus right hand side is numerator. And denominator is the variance of the observed signals. And we determine alpha and beta simultaneously using this likelihood function. And for analyzing the Planck data, we use the multi-frequency likelihood developed in Minami and Komatsu 2020A. For the detail, please read this paper. We first validate the algorithm using simulated data. How does it work? These are from the simulation with future CMB data, assuming light-bound satellite. In CMB channel, this is a contour plot of the determination of beta and alpha. So uncertainty on alpha plus beta is very small. However, the uncertainty on alpha is very large because this is a CMB dominated channel. So there are very small foreground channels. We cannot determine alpha well. So it is very hard to break the degeneracy. And in foreground dominated channel, alpha plus beta uncertainty is extremely large. However, uncertainty on alpha is small compared to CMB channel. However, yeah, we cannot determine beta precisely. In mid-frequency channel, we can use both CMB and foreground. So we can break the degeneracy, and the uncertainty on alpha and beta is small compared to dust-dominated channel and CMB-dominated channels. So using foreground signal, we can measure the cosmic birefringence precisely. And we apply this method to the Planck data, PL3 data released in 2018. The smallest L is 51 and maximum L is 1500, which is the same values used by Planck theory. And we used Planck high frequency instruments, which is composed of 4 channels, 100, 143, 217, and 353 gigahertz. We used these 4 channels. And this information for experts, we used power spectra calculated from half missions because Planck satellites see the full sky twice in their mission, so we can divide the mission into 2 maps, half mission 1 and half mission 2 maps. So to reduce the noise, large noise from the auto correlation, we use a cross correlation between 2 different mission maps. We apply the mask appetite by smooth method with 0.5 degree. This mask is used to blind bright CO region, bright point sources, and bad pixels where Planck satellite did not see the sky. And we also include the I2P leakage, temperature to linear polarization leakage due to the beam. And that the leakage is corrected using quick-ball methodology. And however, if we include this correction, or if we did not include correction, it does not change the result. So that is good news. Yeah, but these are only for experts, information for experts. And before going to the real result with Planck data, we at first validated our result with their full focal plane simulation, FFP10. There are 4 alpha and 1 beta. And we used 10 simulations without foreground samples. We did not include foreground samples because no beam systematics is applied to them. So we can only use CMB and noise maps to validate our methodology. So because there is no foreground map, simulated map, we can check only beta by setting alpha or alpha to be 0, and only determine alpha by setting beta to be 0. By setting alpha to be 0, we can reproduce beta 0 beta 0.01 plus minus 0.03, and by setting beta to be 0, we recovered 0 consistent alphas. So no bias was found. So test passed. So let's move on to main results. The right column shows the main results. Recovered beta is 0.35 plus minus 0.14, which shows beta is positive at 99.2% confidence level, which is 2.4 sigma significant. And other, for example, these alphas, miscalibration angle alphas are consistent with 0 within the statistical uncertainty. And this alpha 100 is consistent with 0 when we consider the calibration uncertainty on the ground calibration of Planck satellite, which uncertainty is about 0.28 degree. So all alphas are consistent with 0. And perhaps you may suspect this negative alpha may induce the positive beta. However, when we remove this 100 gigahertz channel, we can determine beta and alphas, and the resulted alpha is consistent with this value. So this negative alpha did not give a bias to the measurement of beta, because 100 gigahertz channel is very noisy, so removing this channel did not make changes. And this 0.35 is consistent with the Planck's result. The center value is consistent. 0.35 is consistent with 0.29 plus minus 0.05. And when we set alphas to be 0, we can, this is like a similar prior knowledge as Planck's result. So the result T beta is 0.289 plus minus 0.048. So the center value is almost the same as their 0.29, and the statistical uncertainty 0.048 is consistent with their 0.05. And yeah, of course, this measurement should be affected by the same systematic uncertainty, 0.28 degree. However, yeah, without any removal of foregrounds, we can determine beta. We can reproduce their result precisely. This is very good news. And the left figure shows the 2D contour of the posterior distribution of alphas and beta. So the cross correlation between alpha and beta here. So as I showed, the alpha and beta, the anti-correlated. And the degeneracy of alpha plus beta was broken by the determination of alpha. And these are the observed the real EE minus BB power spectra used in this analysis. These power spectrums are from 143 gigahertz and 117 gigahertz. Red dots show the observed EE minus BB power spectrum, and blue dots show the CMB theory power spectrum. So the difference includes the foreground signal. So in small multiple L region, the difference is large, as you can see. So this difference was used to determine alpha. And in high L region, CMB is dominated, so we can determine alpha plus beta in high L region. Next, move on to the real EB power spectrum. EB power spectrum from 143 gigahertz and 217 gigahertz. So this red dot shows the observed signal attributed to the miscalibration angle alpha. This blue is the CMB signal attributed to the conic birefringence beta. So these red dots are rotated by alpha and become this EB power spectrum, and these blue dots are rotated by alpha and beta and shows this blue power spectrum. So the sum of red and blue shows the best fitting model for explaining the data points, black dots. You might see this oscillation of EB power spectrum, which synchronizes the EE power spectrum, which is created by the sound wave acoustic oscillation of the universe. And yeah, let's go back to the EB cross correlation of foregrounds. Yeah, we use the assumption EB cross correlation of foregrounds to be 0. If they are not 0, that would give a bias of the measurement of alpha. If there is a intrinsic EB cross correlation of foregrounds, the alpha is actually becomes alpha plus gamma by introducing new angle gamma. This gamma is the same as gamma is a parameter of the EB cross correlation of foregrounds. So if there is a EB cross correlation of foreground, we can only determine alpha plus gamma from foreground signal. And from CMB, we can determine alpha plus beta. So in this measurement, we can only determine beta minus gamma to be 0.35 plus minus 0.14 degree. So if we don't assume EB to be 0, we can only measure beta minus gamma is 0.35 plus minus 0.14 degree. However, there is evidence for the dust-induced TE cross correlation is positive. TB cross correlation is positive. Then we would expect EB cross correlation is positive by Huffenberger et al. And some other papers show this relation, assuming some models. That means gamma is positive. If so, increased further. So that means we can give a lower bound on beta when gamma is positive. So we can say that this is a lower bound on beta. So beta is not 0 anyway. And what does it mean for your models of dark matter and energy? Positive non-zero beta means what? So yeah, as I said in the introduction, when a Lagrangian density includes a Chern-Simons coupling, this term, the birefringent angle is beta, is related to G phi gamma over 2 and the difference of field values between observer and the raster scattering surface. Mean field value as the observer and the 1-point fluctuation as the observer delta phi ops is the observer's field value and the raster scattering surface is phi bar LSS. So the difference of field values creates a cosmic birefringence. And our measurement is G phi gamma times the difference of field values to be 1.2 plus minus 0.5 times 10 to minus 2 radian. You can use these values to put some constraint in your models with pseudoscalar field. Let me conclude. We find a hint of the parity-violating physics in the CMB polarization. Beta is 0.35 plus minus 0.14 degree. Our new method finally makes impossible to possible. Use foreground signal to calibrate detector rotations. And our method can be applied to any of the existing and future CMB experiments. We should be possible to test the signal is true or only a coincidence immediately. If confirmed, it would have important implications for the dark matter or energy. That's all.
Thank you. Are there any questions or comments?
I had a question. Maybe I missed something, but I was wondering if about the scale dependence of the spectrum. If you go back to the figures, the EB spectrum, yeah, looks like very flat. But is there any scale dependence, or it's completely scale invariant?
Okay. So just now we assume scale invariant beta. Yeah. But yeah, if we assume the spatially uniform cosmic birefringence, that means that should appear the flat rotation of E power spectrum of CMB. So scale invariant. And if the cosmic birefringence is position dependent, that should not appear the scale L dependence of beta. That should appear in the EB 4-point cross correlation. Like us, yeah, that is sometimes so-called CL alpha. Yeah, anisotropic cosmic birefringence is determined using the methodology like determination of lensing potential. They use 4-point cross correlation using EEEB cross correlation and EBBB cross correlation, EBEB cross correlations. So as far as I know, yeah, this L dependence of rotation beta would not motivated by cosmic birefringence.
I see. I see. What about the connection to the your model with ALP? Is it inducing some isotropy as well, or is it?
Yeah. Even without inflation, there should be isotropic cosmic birefringence. So if there was inflation, that creates a spatial fluctuation. of pseudoscalar field.
Mhm.
In such case, we can find some anisotropic
Mhm.
cosmic birefringence.
Mhm.
So it depends on the parameter of inflation, like R, tensor to scalar ratio R. If
Mhm.
the R is very small, we lose the sensitivity to anisotropic cosmic birefringence.
I see.
Yeah, just a moment. Yeah, maybe there should be some. There is no. Sorry, there is no figure. I can show you the dependence on R. Yeah, anyway, yeah.
I see.
So I measure the isotropic cosmic birefringence, and that is created by the field value difference between observer and emission point. So that would not depend on the inflation parameter.
Mhm. Yeah,
Okay.
yeah. I see. Mhm.
That's all.
Right.
Yeah.
All right. Thank you.
Okay. Is there any other question or comment?
Yeah, could you say a bit more about this expectation that gamma is positive? So how justified is this? And what would it take to settle it, to verify it experimentally?
Experimentally. So, yeah. In observed dust power spectra, TE cross correlation is positive and TB cross correlation is positive. And for example, if we assume the Gaussianity of foreground signal, that means EB cross correlation should be positive. But we know that the foreground signal does not follow the Gaussianity. However, yeah, for example, the dust filament is in the magnetic field. Some models like that between Haffenberger et al. Yeah, they show that if they assume dust filament and some magnetic field, the emitted light should follow the same sign for TB and EB power spectrum.
Okay, but they assume a lot of things and then they get something out. How justified are these assumptions?
So yeah, that is not justified, but that explains the TE cross correlation and the TB cross correlation of dust power spectra. Yeah.
Sorry,
so
you're saying the assumption leading to the conclusion that gamma is positive is not justified?
not justified. Yes.
So
So
sorry, this,
with
now
some usual statistics, gamma is positive. But if dust follows strange statistics, which at this moment we don't realize, that might give negative gamma. However, with some usual normal assumptions, gamma should be positive. Yeah, that is very hard to create the model which produced positive TB but negative EB. Yeah. So as far as assume that this gamma to be positive, yeah, this gives the lower bound on beta minus gamma, on beta. that is the thing we can say.
Leon, are you happy with the answer?
Well, I think I should be, as I'm not an expert.
Yeah, but this point is a very good theme for the cosmologist. Yes, many people say that this should be investigated further with some other experiments.
Yeah, does this mean there are measurements that one can do to really settle this?
Really? So, what? Really?
Do you mean that it is possible to perform some measurements that can determine the sign of gamma?
No. Because the determination of gamma is totally degenerate with the measurement of beta. So the uncertainty of beta is large, and there is no value of uncertainty of measurement of beta. So that means they cannot constrain the measurement of gamma. Similarly. So if we doubt positive gamma, we have to prepare some way to reduce the uncertainty extremely. We need smaller uncertainty on the determination of alpha. But however, we have these ways, the uncertainty is comparable to the value of beta. Okay.
Okay. I think okay to invite other questions or comments. If not, okay, we might thank Dr. Yuto Minami again for the nice talk. Okay, thank you very much.
I also thank you for inviting me to this talk.